Okay, this is chapter 16, and it's about, as you see, sheet metal forming process and equipment. We were talking about different types of operations like shearing, bending, forming, deep drawing, hydroforming, and maybe, let's say, explosive forming. These are processes we'll be discussing in this chapter, and with such processes, we can obtain various shapes out of sheet metals, and they may be car bodies, some trailers, furnitures, home appliances, tanks, cookware. So they can all be performed, manufactured with the help of the processes we are going to discuss in this chapter. Sheet metals are highly important. We have different products around us made of sheet metals. Since they are highly, actually, they are stronger and they are lightweight, since the thickness of the sheet metals are very low. So that's why in most of the cases we prefer to use sheet metals instead of blocks of materials. Here are some examples. As you see, cup-like shapes, conical shapes can be produced with the help of sheet metal process. And these processes are mostly performed at room temperature, since if you increase the temperature of these sheet metals, since the thickness is very low, they will easily deform and your overall quality will be decreased. And the first process we are going to discuss is the shearing process. What we do in shearing, actually, we try to obtain a kind of a blank material, and that's why most of the sheet metal processes are starting with shearing process. We first do shearing and then do bending, or we first do shearing and then do deep drawing operation. This is a fundamental sheet metal operation, and I will be talking about this on an actually schematic. This is a nice schematic showing the fundamentals of shearing process. You see that we have a die, and we have a die opening. Right now this is circular. This is a side view, but if you look at it from top view, you'll see that it's a circular die, and we are trying to obtain a circular shape. So our aim is to actually obtain such a shape with the help of the punch, and this is, as I said, the punch. We are applying such a force from the upside, and we are not actually applying it in larger, let's say, time span, but we kind of doing it in less than a second, like we do in forging process. Then what happens, since this punch is smaller than the gap, it will be obviously going into this gap and remove that part of this initial sheet metal. And in order to remove material, we need to have clearance. If this clearance value is 0 or negative, then that means our punches cannot go into the workpiece, into the hole, and we cannot do shearing operations. So for sure, C should be larger than 0, and this is actually depending on the type of material you are using, the thickness of your material, the die radius, the punch radius. So there are different parameters actually affecting this clearance. And what happens once you apply such a force? We have some cracks actually started, as we discussed in the video. Let me clear this part. Okay, some cracks have actually happen at the top and at the bottom, and then they meet at some point here. And this happens also on the left-hand side, and the slug is removed actually. And depending on actually the forces, the speed of your punch, the material, we may have some high quality burnished stones or some fractures on the side surfaces. And this might be important for you. If it's highly important, if the quality of this surface is important, then you should go with some extra operations, secondary operations, so that you have let's say, vertical plane on these side surfaces. You see that we have a rollover dab. It happens due to the actually radius of your punch. And then we have a burnished stone. We have too much plastic deformation here. We have smoother surface, but later, due to these cracks, we have rough surfaces. And this part is called as fracture depth. And we have a fracture angle of this side surface. And at the tip, you see that we have some burrs. Again, the height, the burr height depends on the type of material you are machining. is quite, let's say, brittle, then you may have maybe higher burrs or smaller ones, depending on the quality of your material. And then please ask your questions later, okay? As I said, burr depends on some properties, so also it depends on the clearance. If you increase the clearance, and the height of burr increases. And also it increases with the ductility of the material. If your material is softer one, then you have longer or larger burrs, and as you know, you need to perform some deburring operations to remove these burrs. And there are some numerical analysis on these, say, shearing operation. You see if the clearance is very low, then we will have such wavy surfaces. And if the clearance is too much, we will have again highly weird side surfaces. But if it's fine enough, then we will have much better side surfaces. So in summary, I can say that clearance is highly important. Let's have a look at these descriptions. We discussed, I think, all these. Again, as in the case of other chapters, we have an introductory table. Once this table is over, make sure that you go through this and have some information about all these processes. And in this shearing, what are the important things? The parameters, the shape of our punch and the die is highly important, since they directly affect the shape of the resulting part, whether it's a circular, rectangular, or kind of a smaller square. They all decided by the punch and the die. And the clearance, as we discussed, is highly important. The speed of punching, it determines the quality of your side surfaces. And lastly, lubrication. As in the case of other operations, manufacturing operations, with lubrication, you can increase the life of your die and the punch. And regarding the punch speed, if you increase punch speed, then probably you'll have more burnish zone, and we can say that the edge qualities, surface qualities improved. And we have a ratio for that, actually, the ratio of burnished area and to the rough area. So this is the burnished area, and this is the rough area. So I can say that the ratio is very small, maybe 1/5 of 10. 1/5 is maybe 0.2. So we can say that it's lower. If you want to increase it, then as in the case of burr height, it increases with an increase in the ductility of the material. But it decreases obviously once you actually increase the clearance or once you increase the sheet thickness, since you have more cracks, and once you have higher numbers of cracks, and that will affect actually, that will increase the rough region, the length of the rough region. These are the issues we discussed. And let me talk about some shearing operations. So we have two basic shearing operations. The first one is punching and blanking. In some textbooks, instead of punching, you may see that it's also called as piercing, but they are the same. So it's actually summarized here. In punching, this is the result, okay? We are not actually worried about this remove part. This is the remaining part is important. We are going to use that part in our assembly or other applications. But in the blanking, this remove part is important. So this is the main difference. We use the same tool, same punch, but if you are not using the scrap part, it's called punching. But if you are using the remove part, it's called blanking. In addition to these, we have some other special processes. For instance, if you have some little holes after each other, it's called as perforating. And if you are removing material from side surfaces, it's called notching. If you are dividing the sheet metal into two parts, it's called parting. And if you have a kind of a tap on the side surfaces, but you're not removing the material, you are just cutting it from two edges, so that later you can do some banding operation and have some various features. And lastly, if you make use of some rollers at the top and the bottom, move it over your sheet metal. With the help of the cutting edges of your rollers, you may be cutting it completely, or with the help of your actually material removal, you can easily bend it. and I can show you the slitting here. This is how slitting is performed. We put the workpiece in between these cutters, rollers, and then later the part is actually removed. And I think then we have fine blanking. Let me talk about this fine blanking. I think we have a picture here. So this is the side view of an ordinary blanking operation. But if you do fine blanking, you can see that we have more burnish stone. The quality of the side surface is improved. How we do it? In fine blanking operation, we have these extra pads, and these are called pressure pads. We apply some pressure on the sheet metal so that it's not actually bent a little more, but in the conventional blanking case, we don't have these pads. So once you don't have them, then you'll have such an actually bending, and this will decrease the quality of the blank shape and also the quality of the side surfaces. So if you want to have a fine blanking operation, what we do, we apply some force on these side surfaces so that you'll have a smooth cutting operation on these side surfaces. These are some examples we can obtain with some sheet metal operations. As you see, car bodies can be manufactured with sheet metal operations. So what are the properties of the dies we are using in this shearing operation? First of all, the clearances may be the most important case, and this depends on the type of material you are using, its tempering properties, the thickness of it, the size of it. It all affects the amount of this clearance, but there is a kind of a rule that it's better you set your clearance to 2 and 8% in between some values of your sheet thickness. So for instance, if the thickness of your sheet is, let's say, 10 millimeter, then it's better you have about less than 1 millimeter of clearance, maybe about 0.8 millimeter of clearance value. And another issue is that since we have quite inclined surfaces, they are not perpendicular. What we do, you may perform some extra operations, or you may have a shaving tool at the top of your punch. You see two, let's say, tools are embedded to a single one. This part is responsible for shearing, but the upper part is doing some shaving operation. But if you don't want to have these two operations on the same tool, you may go with a secondary operation and do the shaving later on. Let me talk about the types of dies we can use in shearing operation. The first one is called as compound die, and as the name implies, we can do at least 2 operations in a single station and with a single stroke. This is an example of a compound die. It's quite complicated. You see that there are many items, mechanical elements, and we have springs, some shafts, punches. So we have, this is our initial strip. We want to have actually a kind of an, let me try to draw it here, a kind of an washer. Okay, this is the type of part we want to have at the end of this process. So what we do, let me try to draw it. First, once you move actually the upper hat onto the below hat and continue applying this force, what will happen? This punch actually will push the upper part, and this part will be removed. This part of the strip will be removed, and later on, once this actually stripper touches this upper side, and then our secondary punch will go into this shape, and this part, the hole at the center will be opened with the help of the secondary punch. So I can say that with a single operation at a single station, we obtain this busher or washing. We can also say this is the result, as you see, after the operation. This part is obtained, and at the center we don't have any material. So this is a kind of a nice approach for mass production. If you want to do it with different operations, you need to do many manufacturing operations. And obviously, the manufacturing, the design of this die is quite complicated, expensive. So if it's not for mass production, then you shouldn't use compound dies. But if you are going to produce thousands of millions of this product, then you may consider designing a compound die. Then we have the progressive die. This time we have a single station, but different operations are performed after each other in the same station. And you see that we have a RAM here, and on this RAM we have two punches. We have piercing punch, we have blanking punch. And what happens? The difference is that this time we are using a strip of sheet metal, and we are feeding this sheet metal into this area. This is the way we are feeding it to the left. And once you feed it, firstly, a hole will be opened with the help of your piercing punch. And then once you feed it a little bit, our hole will be going to here at this point. It will stop at this point. And then this pilot of the punch will go into this hole here. And then with the help of the cutting edges here, the size cutting edges of our blanking punch, this part will be removed and we will obtain our washer. Again, it's the same workpiece we obtain with the compound die, but this one is much more useful for mass production, since what we are doing, we are simply feeding it. In the previous one, we need to put blank material, remove it, put once again a new one. So I can say that this one is much better in terms of mass production compared to the same part and the compound die. If you look at the right image here, this time the washer is a bit complicated, so that's why they have more operations after each other. Not just two operations, but many operations are performed on this washer. Then we have the last type is transfer dies. As the name implies, this time we are not using a single station, but we are using multiple stations. We are doing an operation and then removing it and then putting it onto the other, let's say, station. And furthermore, we can have some other cutting operations on this sheet metal. So you can do it by using a laser beam, by using water jet. We discussed all these. We can also cut them by using sewing systems, band saws. We can do friction sewing. We also discussed this one. Or we may use some flame cutting, and this one is especially useful for thicker sheet metals.